who aren't aware of the organisation. The International Energy Agency was founded in 1974 as a result of the oil crisis at that time. Energy consuming countries came together to coordinate their response to oil supply emergencies. They formed a sort of club, and they felt that because it was felt that together they could achieve more than if they operated on their own. The International Energy is an autonomous body, part of the OECD, the Organisation for Economic Cooperation and Development. Its work programme is decided by its governing board, and its governing board is drawn from senior officials from the energy or environmental ministries of the governments that are part of the IEA. It holds ministerial meetings, ministerial level meetings twice a year. There is a staff of about 250 people there, energy experts, economists, statisticians, and the office is based in Paris. So there are 28 member countries, as you can see there. There are 2 additional accession countries, Chile and Estonia, so they're working their way through the process to joining when there will be 30 countries in total. In addition, we work very, very closely with the global partner countries, and 7 of those attended the IEA ministerial meeting in 2011, and most of them attend most of our ministerial meetings. The IEA's programme covers what we call the 3 E's, which epitomise the 3 key elements of sound energy policy. Energy security. Well, modern life depends on energy. Energy security is a necessary precondition for economic growth. In India, we know that economic growth has been increasing in quite high numbers over several years now. It's the 4th biggest economy, and over that period, in fact, whether we look at what energy technology perspective could well become the economy in the world. The production of energy has to be environmentally sustainable. So that's the 3rd part. No nation can achieve energy security on its own, and no nation can successfully cope with the challenges of climate change on its own. So that's where we see the importance of bringing nations together, and the importance of the work programme that we undertake at the IEA to address those issues. A 4th E has become more important in recent years, and that's engagement with our non-member countries. And India is one of the countries that attends many of our committee meetings, and ministers from India attend our ministerial meetings in Paris. So now come on to the presentation proper. I'll introduce first part of the presentation I give. I'll just introduce a little bit of Energy Technology Perspectives 2012. John Topper included some of this, or mentioned it in his work free for free access on our website, and so I hope you'll look out for that when it comes down proper. And I'll finish off with a few slides on carbon capture and storage. And as I said, that will be based on analysis from our energy technology perspectives work. Now, the energy technology perspectives was published in June. Came at a critical time for the world's energy system. Energy demand and prices have been rising steadily. Energy-related carbon dioxide emissions have hit record highs, and the rate of increase in carbon dioxide emissions over the last few years have also been at record highs. And energy security concerns are at the forefront of the world's political agenda. When we did, when we started to do the energy perspectives to 2012, incidentally, this is the fourth, I think. The first one is published every 2 years. It's one of two of the IEA's flagship publications. You will probably have heard of the World Energy Outlook, which is our #1 publication. That's published annually, and I think the 2012 will be launched in this coming week. So that will be available very shortly. The Energy Technology Perspectives is published every 2 years. So it began in 2006. So there's been 2008, 2010, 2012. So this is the fourth one. And the political landscape has changed very markedly since the first one came out. Evidence of climate change, if anything, has got stronger over that period. But unfortunately, at the same time, climate change seems to have, or addressing climate change seems to have fallen further down the political agenda. And all countries that have had problems with the economic crisis and other very major issues that they've had to address as unfortunately taking a little bit of a focus of what is really one of the foremost concerns for the world at the moment, and that's climate change. So, in the energy technology perspective, we look at 3 scenarios. The first one is a case where the rise in average global temperatures is held to 2 degrees centigrade, and we call that the 2DS scenario. There's the 4DS scenario, which is where the temperatures are held to 4 degrees, and this is a dangerous scenario for the world. This is a very different world from the one that we're living in now. The 2 degree scenario is what we call our sustainable scenario, where the world doesn't change radically. The 4DS, we're starting to look at really radical changes, and the third scenario, where it's our sort of our business as usual, I suppose, scenario, that's the 6DS, and that's the one where we get very devastating results for the world. So the 2DS, that is where we look at policies and technology improvements. It gives us an 80% chance of keeping the world average temperature And that is where we need to halve energy-related CO2 emissions by more than a half between 2009 and 2050. So we have to reach, before we get to 2050, we have to reduce emissions by more than a half. There are about 30 gigatons energy-related CO2 emissions per year now. Business as usual, the 6-degree scenario, we're looking at doubling that. So we're hitting around 60 gigatons a year. What we need to aim for is halving the energy-related CO2 emissions. So we're looking at 14, 15 gigatons per year. And that's a huge challenge. But a sustainable future, it's not just about reducing carbon emissions. It's about improving energy security, harvesting more indigenous energy for various countries and regions, and creating lasting fuel savings over that period. And so it's also if we look at the total picture, the most economically favourable way forward as well. So what did our results in ETP 2012 show? Are we on track to reach a 2 degrees CDS scenario? Well, the simple answer to that is no. Our business as usual case is we're heading towards 6 degrees, and if all policies and all pledges are put in place by governments that they have announced over the past 2 or 3 years since the COP meetings in Cancun and others, then we're looking at 4 degrees. So 2 degrees is what we want, what we ideally aim for scenario. The 4 degrees, if pledges that have been made by countries are all in fact put in place, and the 6 degrees is actually where we're headed at the moment, if they're not put in place. So can we get that on track for the 2DS? Well, yes, we can. The technologies are there. The possibility is there to do it. The problem that arises with meeting 2 degree scenario is not so much the cost of doing so, although it's very expensive investment-wise, but it's how the costs are shared both over time between now and 2050, and also geographically. And those are the real difficulties. It's how we share the cost over those between countries, between regions, and over time. Because what we see is that the actual costs to do this are very much front-end loaded, and you'll have heard from what John Topper was saying just a little earlier, that CCS is not moving forward as quickly as we would have hoped it would have done just a few short years ago. And that's really because we're looking for large sums of money, and because the technology is not a commercial possibility or not a commercial technology at the moment, then we're looking for large sums of public monies to put it underway. It is urgent that we start to address this. I think that countries are very well aware of this at the COP meetings at Cancun. The majority of countries that attend those, and many of the countries around the world do attend those meetings, they say that a 2-degree scenario is their ambition. Halving the CO2 emissions over this period of 2050 is what they would like to do. Unfortunately, it requires action, and that's what's not being moving forward in the way that it should be done, that it needs to do. So, what are the recommendations that we made to governments in that publication? Well, it's clear, it was made clear that investing in the transition to a clean energy future will pay off. But and 3 recommendations. So, firstly, that we need to ensure that energy prices reflect the true cost of energy. That means removing, for example, fossil fuel subsidies which were in 2011 almost 7 times higher than the support given to renewables. So a very high subsidies still on fossil fuels on a global scale. So we need to level the playing field, essentially, to move forward to a clean energy future. Second, governments can unlock the incredible potential of energy efficiency. And if you look on the IEA's website, then the IEA puts forward 25 recommendations for energy efficiency. And we recommend very strongly for countries to adopt those. And thirdly, we need to accelerate energy innovation and public support for research, development, and demonstration. If there's not public support moving forward, then it won't be there to encourage the private sector investment that's very clearly needed. So, how do we clear the obstacles on the road towards a clean energy future? Well, a sustainable energy system is smarter, more unified and integrated is an energy system. Today's system is centralized, and in most countries in the world you can see this. It's a centralized energy system. It's one-directional. What we need in the future is a decentralized, multi-directional system. Complex and diverse individual technologies need to work as one. Technologies need to be deployed together rather than in isolation. And policies need to address the energy system as a whole rather than individual technologies. So, success will hinge on systems thinking, and a number of countries are also thinking about this now, where their transmission and distribution systems may have been developed in the 50s, 60s, 40, 50 years ago. Now they're looking at, and there's a lot more renewables being brought into play in many countries. It's been quite difficult to get those renewables feeding into the energy systems as they are in many countries of the world at the moment. So that needs to be addressed, and that's important. Let's look at a number of energy sectors, and you can see the circles as they go.
One of the graphs we have indicated that efficiency of the plant versus CO2 intensity factor, like for subcritical, supercritical, advanced and supercritical, and the efficiency is going to increase. At particular CO2 intensity factor, once the carbon capture was installed at the plant, the efficiency was shown that it is in decreasing trend.
That one or that one?
Like for subcritical, it was shown that, for example, 95% of efficiency. For supercritical, it is showing on the x-axis. And once that CO2 intensity factor was reduced, why the graph is turning back? It means that efficiency of the plant is going to increase.
You're saying, why does that cut back like that? Yeah, that's to just illustrate that when you apply carbon capture, then you have an efficiency penalty associated with that. Now, at the moment, it's 7 to 10 percentage points. So if we have a plant here, average at the moment 33, then if we put carbon capture on, then that would go to 23 points percent efficiency. Now, in the future, research and development work on demonstration plants will, it is assumed, reduce that efficiency penalty. So the efficiency penalty, by the time we install an advanced ultra-supercritical, we're looking at here, say, 49% to 45%. So we're looking at bringing that 7 to 10% down to perhaps 4% percentage points penalty on the efficiency. So that's why that's why it goes back like that. It's that the efficiency of plant X here at 40% will, if carbon is capture is applied, the net efficiency with the capture plant on will be less than 55, for example. Does that answer your question?
So what is the reason behind it? Once I reduce the CO2 losses, the efficiency of the boiler will increase. But here, once I reduce the CO2 intensity factor, my efficiency of the boiler is reducing.
Well, why does the efficiency reduce when you have capture? Well, it's the net efficiency of the plant. So it doesn't affect the efficiency of the boiler or any of the system, but to operate the carbon capture plant takes a significant amount of energy at the moment, and so the net energy, the net power from the plant will be the efficiency of the base plant minus the efficiency that it takes to operate the capture plant.
Solar PV, 27% annual growth in wind. So on track we have the green, we have the renewable power. Fuel economy, electric vehicles in industry are improving, but much more effort is needed. But when we look at the others, when we look at clean coal, nuclear, CCS in both power and industry, our building sector, and biofuels, then clearly we are not on track. So those are areas where we need to work. I switched off the ringtone, but clearly when something happens, it must disturb itself. Okay, so let's look at some of the sectors in a little more detail then. Look at low carbon electricity. And you can see very clearly where we are at the moment. Fossil fuels dominate quite clearly with coal, gas, oil. You can see for electricity they are dominant at the moment. You can also see as we move forward how things need to change. So you can see that the fossil fuels will reduce quite markedly by 2050 for our electricity generation. The majority of the big increases need to be seen in renewables. Natural gas, if we look at natural gas again on a global scale, we see that gas is, I mean, you can look at the United States, for example, but in many countries of the world, the use of gas is increasing. And in the short term, this has an effect on the CO2, because if you look at state-of-the-art technologies for coal-fired power generation, state-of-the-art for gas-fired generation, then gas produces less than half the amount of CO2. So in the short term, moving towards gas for power generation is a positive move as far as CO2 emissions are concerned. But as we move forward, and you can see there around about 2030, things start to change. Then all the gas that is put into operation, gas then becomes a part of the problem, because it's still a fossil fuel, it still emits CO2 when it's burned. And when we get to around 2030, we're still needing to further decrease our CO2, the global CO2 emissions, and gas then becomes high CO2. So then we need to start decreasing our use of gas as well. And another thing that we have seen recently, phenomena throughout the world, is the increase in use of unconventional gas. And throughout the whole period, from 2009 to 2050, so over those 4 decades, then the use of unconventional gas will continue to increase. Look at another sector, industry. Well, industry must, if one needs to, enhancing energy efficiency is key to accelerate the development and commercial development of new technologies, and to promote standards. Incentives and regulatory reforms are required, so that we can use the best available technology in new plants. Well, in new plants, particularly in non-OECD countries, and in refurbished plants in OECD countries. So industry must cut direct emissions over the period to 2050 by 20%. CCS is a critical technology also for industry. And reaching the 2 degrees, scenario requires you to spend more than $10 trillion between 2010 and 2050. And so, just as a final slide on our energy technology, just on a summary of the energy technology perspectives work that we undertook, looking at the investment required. So we're looking at almost 40 trillion, I think about 36 trillion US dollars in additional investment will be required. See that the fuel savings far outweigh the investments. The difficulty on the back-end loading, and that is a key challenge to overcome. If we look at the total savings that we get over that period, then you can see even if they're discounted at 10%, then there are still savings. It still produces a savings over that period of time. So, on technology roadmaps work. Well, the technology roadmaps, what are they? We look at technology today, and where are we? What are the technologies in use? How many gigawatts of installed capacity, for example? What's the cost efficiency of what we have in our system at present? Then we look at the deployment pathway needed to achieve the 2050 goals. Remembering that our ambition is to achieve the 2DS, the 2-degree scenario. And then once we've done that, we look at the priority near-term actions. What do we need to be putting in place in the next 5 years? R&D gaps, what are they, and how can they be filled? What barriers and obstacles are there that need to be overcome? What are the market requirements and policy needs? And the international collaboration is a key component, and what areas can international collaboration help in achieving the goals? But the IEA's development of technology roadmaps came out of a request from the G8 some years ago, and we started producing our first technology roadmaps in 2009. And I think the first one that was published was one on CCS, which many, or some of you may have seen. As I mentioned earlier, all these roadmaps are available free on the IEA's website. So if you just log on to the last 3-4 years, we've published, I think now, about 16 or 17. Most of them look at the global picture, but we do have 2 national roadmaps, one on wind energy development in China, and one which is coming out, I think, over the next, before the end of this year, on the cement industry in India. So there's one particularly focused on India and the cement industry, and that's coming out. But the one that I'll talk a little bit more on in a moment is what we call the Heavy Coal Technology Roadmap, HELE. I'll just say heavy as I go through. Waiting for its publication, which will be very shortly. The analysis that was done for the energy demand, you can see that very clearly from the graph in front of you. Between 2000 and 2009, demand for coal grew by 42 exajoules, far exceeding the increase in demand from all non-fossil fuel energy sources combined. So 42 exajoules. If we compare that to nuclear, it grew by 1.2, biomass and waste by 8.4, hydro by 2.3, renewable energy technologies by 1.7 picojoules. So you can see that the mix of fossil fuels in a country is it's driven mainly by its availability and domestic fuel prices. This one, I think, shows you more clearly how coal use has been increasing for years. You can see this is nuclear, the growth of nuclear over that period, the growth of hydro over that period, and the thinner band here is non-hydro renewables. So you can see the increase in increasing the capacity of non-fossil sources for power generation over that 20 years. But this is the issue. If we look at the share of non-fossil electricity, so the share of these to the total, it has been in steady decline over that period. So that's a huge concern. Countries globally have been making huge efforts and have had huge programs of installing wind, solar, increasing their hydro, etc. But even so, even though they've been increasing at this rate, the share has been in steady decline. Whereas we look at coal has steadily increased over that period. So this is the challenge that the world faces in meeting a 2-degree scenario. It needs a much greater focus on increasing the renewables if it's going to, because when we look at the share of coal increasing, this essentially means CO2 increasing over that period. So coal, well, it's why does everyone use so much of it? Why is it going to increase at such a rate? Well, global recoverable reserves are estimated at around 1 trillion tonnes, which is sufficient for a further 150 years at current consumption rates. Recoverable supplies of coal are to be found in around 75 countries. So if we're looking at energy security concerns, coal is one of the fuels that doesn't really provide one. Many countries have recoverable resources. It's a cheap, low-cost fuel, and it's particularly suited to large-scale power generation and to many industrial applications as well. What are heavy technologies? Well, here I've tried to just explain what they are. In the roadmap, I just talked very little about CCS. I mentioned that in the roadmap in 2009 there was a CCS roadmap published. Our CCS unit at the IEA are terminating that and relating it to reality as it is now, as changes as we've seen 3-4 years since that was put underway. So early next year there will be an updated CCS roadmap. So here I'm talking about this part of the system, and mainly this efficiency improvement. We know that with coal, conventional emissions, local emissions are also important, and we can't get away from that, so I have included parts of that in the roadmap, but the focus, as with all the roadmaps, is how we achieve, or what we need to do for that particular technology, what is the contribution of that particular technology to achieving the 2-degree scenario. So, efficiency improvement, there is a lot of scope, as I'll come on to, for efficiency improvement, a lot of emissions savings that can be made. However, as John Topper noted in his talk, if we are to make deep cuts in CO2 emissions, both in power or in industry, then CCS is essential. But it's not a part of the, or a central part of this room. I should also say that efficiency improvement, they don't just give us, it's not only the lower CO2 emissions that we focus on. If we improve the efficiency, we reduce all emissions. So if you raise the efficiency